Good morning, everyone. Thank you for your interest in joining the webinar. Today, we are going to explore a very commonly used feature of this SAFE program, which is the foundation, analysis, and design. So in this webinar, we are going to take up a couple of examples that specifically uh, on the foundation systems. One is for raft modeling and analysis, specifically on combining multiple models, multiple EABS models results into the SAFE for the combined footing analysis. The other one will be a simple example that will be focusing on the uplift of the foundations. So the SAFE can handle both of these common structural engineering problems. We hope you will find this both information and helpful. Let's get started. Let me take you through some of the slides to explain a few things. So some of you may be new to the SAFE program. What is SAFE? SAFE is a specialized structural engineering software focused on floor system, foundation system, their analysis and design. Right? It is developed by CSI, part of the suite of structural and earthquake engineering tools. And it is basically a standalone software, but it is kind of a supplementary tool that supports information transfer from other programs like EABS, SAP 2000, CSA Bridge, for this specific purpose of analysis and design of floor and foundation systems. The core strength of the SAFE is it is very similar to the other softwares like SAP 2000 and EABS, which you probably be using in your design offices. The interface, and you'll find many similarities between the EABS and SAFE, and it uses a common Sapphire solver. So many of the features that you'll be using will be very much identical almost. So basically the core strengths are the full integration across workflow. That means you can model the finite element model, analyze, design, and you can also perform detailing that can generate drawings. So it is a complete package in that integration of various aspects of your analysis and design. Then it has a powerful finite element solver, which is called Sapphire, which is used across other CSA products. And then it has a flexible geometry and modeling, which we will explore today. It has soil structure interaction support. The other aspect we are going to use in this presentation. Other than that, for the floor slab system, we have post-tensioning along with the standard reinforced concrete slabs. And we also try to explore the detailing features in today's session for the foundations. Right. Now, for today, we have taken up the foundation system. Specifically, the slab system will be covered in another session. So the first one would be about a complete model, but we will take two EABS output of the loads from above, and then we'll try to combine how to do it in the SAFE. And we'll also explore the modeling tools available for creating such a combined raft. And finally, we'll perform the analysis and design of the system. Next example would be an uplift analysis, right? So these are the tools we'll be using commonly for any model. we'll be starting with the section properties, spring properties for defining the soil springs, and various drawing tools listed below. Now, let us start with the first example. I have listed the steps how to combine the models in the SAFE program. So what we are going to do is we'll jump to the software as well, and then we'll come back to the slides once again. So we have a sample model that represents block A. There will be another tower block B. It can be multiple other towers, but for the demonstration purpose, I'm using only two. So block B will be mirror of this model, and it will be placed on the right side of this model at say 100 mm apart. Right. So this model is run and the export is done as usual. The export story as safe v12.f2k file. F2k file is the text format of transferring the information to the save program. So the story will be the base, and then the option we used export floor loads and loads from above. And I have selected all the cases. So basically the case results for these listed cases are to be exported as loads from above. Next, we will jump to the safe, and then let's come back to the slide and view the steps. Step number 1 is import the respective F2K files. We have two F2K files from both models, and then we will be saving them as individual FDB safe model files. Let's call this as model A and model B. That is step number 1. Let's go to the import save F2K text file. And we have the F2K file for block A. We'll do a save as. Give a name and save this model. Let's import the model B. All right, step 1 is complete. Now let's go to the step number 2, which is exporting the model B using file export save database tables to text option. At this stage, we have certain options that are optional only. but I'm not going to do that. What you can also do at this stage is you can rename these joint labels as you want with the help of interactive database editing tool, or directly right-clicking on the joins, and maybe you can prefix or suffix with some more alphabets or identification. Basically, that would be different from other, but it is only optional. The second thing what you can also do is you can move this entire system positioned at the exact position in the combined model. So two things, and both of them are optional. We have options to handle that in the import of this model, right? Now let us do the step 2. This is export, file export, and save database tables to text. This is also an F2K file export, but this export requires these tables to be selected, as I shown here. Basically, all the tables except the grid system I'm trying to export. Simply exclude the system data and then all load patterns. This I will call it as with a suffix, something to identify with, ETT. This export tables to text, and the type is .f2k. Okay, this is important because if you want to combine the model, program can recognize this kind of text file through this particular option. That's why we are doing this. Save database tables to text option, right? Now we are going to combine. For that, I'm going to create a new model. So I have my separate FDB file for the model A and then model B. And then model B was exported using that database table export option. Then now I'm opening the model A and do a save as, so that I will relabel the name as AB combined. Right. Correct. Now third step is complete. The last step is importing the F2K file we just exported. Let's go to the file once again, import. This time it would be save database table in text file option, right? It is a similar one which you used in the export. For the export, now we'll find the similar one in the import. We'll use this and we will select add to existing model. And then we have advanced options, which we require. There are 4 tabs. First one is the message control. I will tell do not abort In case of any errors and warnings, we will review them, if any. And then next tab, items with same name. Right. So these are the three main tabs that we will be dealing with. First one, we have done it. Message control. Second one is items with the same name. The settings for this will be the default one, except that we're going to use replace item in the model on the other items. So the important one here is the add database element to model with new name. Right. I will show you what's happening once we have imported with this setting. And then the third is coordinate transformation. That means the model that we are importing and its position, basically from the global origin. Right? You can also rotate if needed, because typically individual models in the ETABS will be modeled from the default origin 0, 0, 0, but in the combined position, it will be different. Right? For that, we are trying to position it. And then items in the same location, there is a specific tab for that. Set the default one is allow duplicates in the same location so that you can modify it after import. I'm leaving to the defaults. In our case, there are no objects in the same location, so it will not be useful for us. And the last one is coordinate transformation. For this one, this is equal space span of 5 meters, so 25. So another building on the right side, it will be 25 meters, but it is spaced 0.6 meters so that the columns will also be spaced. So you can work out how much is the separation, the clear separation, and work out this. I'm going to give 25.6 meters. Okay. Okay. And which model to import? The ETT file. We just exported the model P. Right. And you can see 0 errors and 0 warnings. And you can see some of the information, for example, joins. So there was a point object of same name found in the model B. Then it is renamed as the name existing name and a suffix of -1. Right? This we will see that happened for several other point objects. That's okay. Now press done. Now you can see. Let me save this at this stage of the operations. And then we can go to display and show loads, joint load. So for those who are new to the SAFE program, imports the loads from ETABS model with a load pattern suffix underscore above. for each case like this, and it also creates the load pattern in the same name as that of the EABS model. And then in the load case, these two are combined. So any modification and additional loads applied can be easily applied in two separate sets of load patterns, right? But generally, in addition to the foundation existing loads from the loads from above, we can also add some uplift pressures, soil, sustained soil on the footing, etc., or other live loads acting on the base mat, etc., can be applied directly on the objects. So for that, you can directly use one of these patterns. Above will be the imported loads, right? So generally, you don't have to worry about these segregation program handles this completely for you. So what we are trying to show here is the loads imported. Can you see? All right. Let me close this window and have only one window so that the graphics will be clearer. Let me also make sure it is standard graphics. Preferences, increase the font size a bit. Yeah. And set display options, I'll enable the joints. Right. Now with this, I will also show the point labels. Right. If you focus anywhere, so the model A was created and created a copy of the model A for creating the model B. So the IDs are the same. So this is purposefully done to demonstrate this. So you can see 44, this is 44.1, 132 or 110, 110-1. So the relabeling is done automatically by the program during the import. All right. Now let's move to the next. Right. Once we have imported, now we'll start with the drawing tools to complete the raft model. First, we will be updating our grid system, which is going to help us in many ways. So I'm going to do edit grid system. You can have more than one grid system. Let's use the global one, the current one. So we'll select these joints and update the grid system. Add grid lines at selected joints in both X and Y to the grid system. All right. Right. And at this junction, the separation of model A and B is 600 mm, but I want to keep this F grid at the center of these two joints. So I'll update the grid system. So it's got as 25.3. All right. So next, we will prepare the properties required for this. So I'll start with material properties. So you can, these steps are similar to that we do in EABS, very much identical set of procedures that you will follow. But I'm going to use the default CS30. It is about M30 grade. It's okay. And then the rebar material, uh, let's say FE400. You can update this or create new one, but to save some time, I'm going to use these materials and then move to definition of the raft or the mat. Let's modify this existing one. Let me call it as R let's say 750 mm, and the property type is matte and 750. The modeling type I'm going to use is the default shell thick. One more definition would be the spring properties. From the GI technical report, you need to find the soil subgrade modulus, which will be applied as area spring to this raft. And program uses the Winkler soil model, soil spring model for the analysis. We'll update this, let's say approximately 200 SPC, and for a settlement of 10 mm. Say this K value for the local 3 direction of the area object, which is perpendicular to the area object. And local 1 and 2 will be in the in-plane directions of the area. You can assign some stiffness for this, which I'm doing here is applying some 10% of this. It's an approximate, but if you have an exact value, then you can update it. The other ways to model this is to assign restraints at the corners of the mat or the footing in terms of rigid restraints or point springs or line springs. So any of these modeling of the lateral support will be helpful, right? And then I'm going to use a linear option here. We'll see this in the uplift analysis of this works when it is tension only or compression only. The program allows you to also model the specified stiffnesses in a nonlinear case. But in this example, we are going to restrict ourselves only with the linear static analysis. So linear springs are fine. That's the soil support. Let us quickly create this raft. Will be one single raft, right? Let us say the shells expand by 2 meters on all 4 sides. I'm using this option to achieve that. And then this raft is assigned with assign, shell, and area spring, which is the soil support, also assigned. At this stage, I will update the grid system one more time. This will be useful for my other modeling. Specifically the design strips. Right. Save this. The next step would be the drawing design strips. Now the program for the design has 2 design bases. One is the finite element base. Even if you don't draw the design strips, your design will be available for the element by element basis. That will be a simpler tool, but our recommended and widely accepted method of design would be the strip design. So we need the design strips to draw all over the slabs, covering the entire slab. Now, if you look at the size of this, it would be very difficult for you to draw manually, because drawing a strip will be, you need to specify the width on the left and right, and that forms total width. For example, here it is 1.5 meter and 1.5 meter on the right. I mean, the left and right, so that forms 3 meter wide strips. So you'll have to decide on this. So but the strip widths are arbitrary, right? You can decide on the width. Some people will use conservative 1 meter wide strips. Some will consider multiples of the depth of the raft, 1 to 2 times. That is also fine, but that is up to the designer to decide on these. So basically, the design strips are non-structural elements or geometry drawn all over the raft or the slab cover entirely and get the integrated forces for the design. That's the purpose, and it also performs the design in the end. Now, the drawing, instead of drawing individually, I'm going to show you how quickly you can utilize the grid system. That's why I was preparing the grid system for my requirement. Let me show you how to do it. Now, under the edit menu, you have options. You can see add, edit design strips, add design strips using grids. And then I will use this for creating X directions. And these strips are grouped under layer A, and one more layer for the Y that would be grouped under layer B. Let's start with the X and layer A, and then you can ask the program to use a fixed specified width or auto. And you can also include the middle strips. We typically use the middle strips here. Most cases, because we want to have a smaller column strips. So column strips are those strips running on the column line, and middle strips are space filled by middle strips between two column lines. You will see this in action. I'm leaving it to auto. Auto means it will take 0.25 on the left span. So this is 5 meters apart, equally spaced. So it will take 0.25 into 5, which is 1.25 on the left and 1.25 on the right. Right. This is X direction. So these are horizontal ones, and these are kept as layer A. And if I press apply, so program can quickly create it for us. Now let us see this with a better output. For example, I'll ask the program to show the labels and show widths. See, program has created. So the pink color ones are column strips. The yellow color ones, those patches are the middle strips. If I right click on any strip, it will carry the information of the geometry. You can see 2.5 on the left, 2.5 on the right. That makes 1.5 on the left, 1.5 on the right, and then it is 2.5 meter wide strip. It can be varying also depending on the model. And then for the design, it can carry other information such as what is a strip. You can click on this, and you can also update this for a particular rebar material, just different from this. If you want, you can create and add this. So we are treating all the horizontal ones as strip layer A, and this particular one is column strip, mid strip, right? You can update this later through the design overrides whenever you want, or right-clicking on individual strips for a particular strip. The former is used to handle multiple, the latter is to handle one at a time. All right. So here, one small change which I'm going to make is to remove this particular strip. Middle strip And then I'll update this last strip for its geometry. So on the left, it is 2 meters and 2 meters. Now see, it is fully covered now. Same will do for the bottom also. Right. We save this and then we'll go for the same add design strips. And do the same for Y direction. Here there will be something different from the previous one. That is, it is not fully covering because there is a change, a new model has been imported. So here program is having some difficulty because the spacing is also suddenly changing here. So we will fix it in a different way, but I'm doing it purposefully to introduce you to the other drawing tool, which is called the support lines, right? So I'm going to handle this support line in the new portion of the combined model. I'm going to draw support line. Support line is also again a non-structural geometry that is drawn to help the user to create strips and other slab panels. The next one, which we will cover. This is one step advanced than the standard grid system-based auto design strip generation. I will show you how it is. So this one strip is for B. So I'm using B layer for the Y directions. I'm going to draw a support line from this end to this end. So we need to do a bit of work on this design strip generation. That is the important task in the SAFE program. So you can see this strip. I'm selecting this strip and I'm going to the edit. Again, add edit design strip, but this time I'm going to use this strip. I'm going to tell the program, don't create middle strip and use a fixed width of 2.5 meters like others we are maintaining. And you can see strip is created. Let's close this. Now let's select the support line once again and replicate it in other locations and do the replicate. 1, 2, 3, 4, 5 meters apart, 4 times, and apply. Now you will see how quickly program can create this design strip. Add design strip. This time I will include middle strips and leave it to auto, and then press apply. And you can see it even extended beyond this point, which is not 1.25, it is 2 meters. Strips are created. This one last update for the B is this end, where it has to be 2 meters and 2 meters. So this is how quickly you can create the design strips using the support line as well as the grid system. So a grid system is going to help you significantly in your modeling. Now we can run the analysis. Just before that, let me ensure one more thing, which is nothing but these new joints and the current ones to be included in the meshing, which I ensure by specifying it as an assignment. Assign joint floor meshing option, include apply. And I right click just to ensure all the inputs are fine. Now we can Under the analyze, the default F5, which is run analysis and design. So let us update the design preferences. So let's select the code. It's 456. So the factors and the options. Um, so increase flexural rebar for enhancement concrete shear capacity. By default, it is no. We don't want to let the program increase the flexural rebar for satisfying this requirement. Any one-way shear check and its rebar requirement will be handled by the designer. That's what we want. We will decide on that. And then ignore beneficial PU in slab design. Yes. And then pattern live load factor. We are not using it here. That will be useful in this slab design. And the cover for the slabs, say 50 mm for top and bottom, and preferred bar size of 16 mm. The inner slab layer will be layer B by default. That means layer A in the bottom face. If you say layer A, that is the outermost layer, and the one perpendicular to that will be layer B, which is in Y direction. That will be inner. So layer A will have a different effective depth for the design. Layer B will be slightly lesser than that because of this rebar arrangement, and that will be obtained from these values above. All right. Well, that's it. And then we have the load combinations. I'm leaving it to the program, but for the service limit state, I'm going to create a few. So dead live, a copy of it to dead live and EQ, add a copy of it, dead live EQ negative, then 3, this one will be Y, and the last one, add a copy of it, Y negative, and you can create any other combinations that you want. Right. Design combinations, I'm leaving to the program for the IS456. I am going to hit the analyze and design. All right. Now we will start with checking the outputs under the display. Show deformed shape, that is for the settlements. Obviously for the combination output of COM1 to COM31. You can see settlement. So the contours can help you with the values directly in the graphical window. And then you also have the left bottom maxima and minima values. So the minimum, which is the downward settlement, which is negative 4.7, which is okay. And combination 2, which is for the EQX, which is seismic force, positive, negative, and Y positive and Y negative. Then the next output under the show force stress diagrams will be this soil pressures. This is about 100 to, and while it is displaying the soil pressures, the maximum and minimum will help you in identifying the uplift, if any, in this. For this particular case, you can see the maxima is minus 32, minima is minus 98. That means both are under compression, so no uplift. You can check this for all 105 and 32, negative both. It's a symmetric building, but we will check the uplift effect in the other model. For now, there is no uplift. We are moving to the next. It's nothing but the design outputs. Now we can go to the show slab design and display. So the design base will be the strip based, and then we look at the layer A first. Let me ensure it is visible. Right. So in the modeling, you have the option to include the stiff area object that you can introduce at the column locations that will form the junction, the stiffened junction of the column on the raft. In this one, I did not, but with that, there will be a difference in the reinforcement, which will be reported at the face, where there will be higher compared to the stiffened portion of the raft. Right now, let us see for layer B. Right. You can select objects, keep them only in the view. All these controls are available. I'm leaving it for you to explore. But what it basically gives you is a control how we want to see this. I think, yeah, it is currently displaying rebar intensity per unit width. It will be easy for you for the detailing purposes. Then next output from the flexural reinforcement is the shear reinforcement. That means the program performs the one-way shear check, basically. It should be noted that program performs this at each station location along the length of the strip, not just at D away. This is to ensure that in a complex raft system, the shear can be significant. It's not always checked at D away, but it could be arising from other nearby loading point. So program does this. What the user is expected is to decide on how we're going to uh, provide the shear reinforcement. For example, if I focus on this, so this is the column location, and the column face will be somewhere here about, let's say this is 500 column, so 250 from this face. And from here, you have to see a D away and see whether beyond this point, rebar is required or not. If required, you have to provide it in terms of stirrups, or else it will be ignored. It can be ignored. Right? That way, you have to do the detailing for the one-way shear. Or you can also enhance the flexural reinforcement locally to check it. So it's kind of detailing plus design together. So the user will have to decide accordingly. Right. The last one on this output would be the punching. Show punching shear in, sorry, punching shear design, which will be reported like this as a ratio of demand capacity, not as a stress. So any ratio less than 1 is okay. So locations where a beam element, which is the equivalent wall element, the program converts it as a beam element for the safe modeling. The program cannot report it because there is no design procedure available in the codes. And then for the joint locations, program will report. Right. It calculates the effective punching perimeter, then the depth, then finally demand to capacity ratio that is displayed. All right. And the last thing here in this one would be the detailing feature they want to cover. So basically, the detailing is based on all the preferences you set for the detailing. So under the detailing, bar selection and curtailment rules, we'll go for the slab, mat footing option. And then we go for the mat, this one. Recall the slab property we specified as mat. So it is going to use this setting for that. You can also set enforce minimum reinforcement. There are no openings, so you can ignore this. Basically, the edit rebar selection rules. Here you'll set the smallest and largest bar size, say 12 and 12. Preferred bar size, let's keep it as 16. Obviously, this comes from the experience, and some defaults settings for these will be based on globally used spacing and bar sizes. So you can modify these as needed. So minimum spacing is 75, maximum is 450. That should be okay. I'm going to detail all the bars or only typical bars above what is specified here, the way you want. And then we'll perform the detailing. There are two things. One is the detailing itself and then the drawing management. So drawing management is where you'll get options to export to the CAD as well as the BOQs. Let us first perform this. Right. Now this will open another form where you can interact through the Explorer. For example, details, plan views. Let's go for the plan view. Particular one will be top. Increase the font size a bit. This is bottom bars, bar location, right? Sections, all right. These are all components individually that you can view, update, or um, before finalizing for the drawings. Then come back to the drawing management, the end, and open drawing manager. So whatever we have seen, or you can again see this in the component, but additionally you will find user drawing sets. Then you can use any one of them to add new drawings. I'll simply add views to the drawings by right clicking on this, and this will be a slab story, and you'll have to select what are the drawings you want to have. I want to have the top, bottom plan bar details, and then I'll have a couple of sections. Then I will have tables that would be for BOQ and bar weights. Okay. Expand this. Now you'll find all of this here, right? You can modify this, you can right click and update the scales and other things. So all of the options are available, but ultimately what you can also do is export this drawing sheet um, to the CAD program. If AutoCAD is there, then DWG file, or else you'll have the DXF file. So you can select what are the sheets you want to export, right? You can export and then open it in the CAD program. So at this, I will stop before going for the last one. Yeah, I forgot to show one more item here. Yeah, the BOQ will report as well as rebar weight summary based on sizes. It will not give the bar bending schedule, but these two informations will be available when the drawings are generated this way. right? Now let's move to the next example, which is the uplift analysis. I'm going to show a simple model, but just to give you the concepts and how will we use this. For the uplift analysis, we need a nonlinear static load case to perform this because the soil is going to be nonlinear in terms of compression only effect. And then the convergence is the key for the analysis. If convergence is not happening, then there is instability because of the loads. You'll have to address it differently. And uplift analysis is a nonlinear type, right? So the response spectrum analysis, because of its nature of the method, its results cannot be used here because it has lost its sign and direction. So they should not be used in the uplift analysis. However, for the foundation, specifically for this foundation system, you can always convert this response spectrum as a user load in the EABS model itself as a linear static, and then use that result in your foundation design. That is the simplest way of doing it, and it's our recommendation for specifically for the foundation systems, right? Let me jump to that model. I will show you. It's a very simple model just to give you this. All right. This model is created certain loads that will create the uplift for demonstration purpose. But in your real model also you will find this uplift pretty common. Let me run the analysis and I'll show you. It has a dead load, live load, and then the EQX, which is a seismic load. All right. These are the linear static cases, but it is always recommended that you perform the linear static cases first to identify any uplift is happening in the model, which you can find from this pressures. If I go to you can also find it from the deformed shape as well. If I directly go to the pressures for the combination, this comb1 is gravity only. And you can see minus 55 and minus 67, no uplift. And if we go for combination 2, which is including the seismic, and you can see it is minus 134. And here it is about 20 positive. That means it is in tension, right? This portion of the slab up to this, the dark two blue colors, up to this, it is an uplift portion of the footing, right? Now to handle this, we unlock this model. I'll create a combination for the design purpose. D is for the design. Then I'll put the factors 0.2, 0.2, and 1.2. And then I will convert this combo into a nonlinear case, which you can also create directly, but this will be much easier because in a actual model you'll have plenty of design combinations, right? So we need to select all of them and convert combos to nonlinear case. That is step number 1. And if I go back to the load case, now a new a new load case has been created. We'll explore it, and you can see dead live 1.2. Then importantly, it is having the nonlinear static case type. And we don't want any P delta for this. And that's it. Now we can run the analysis. Yeah. So before that, let me just check the soil spring assigned to this, right? And you can see it is using compression only. Previously we used an linear. Now we are having a nonlinear case, and for the case, this soil property will be compression only. This is another important one we need to ensure before running the analysis. Let's hit an analysis and design. Go back to the pressures. You can check this particular case. Yeah, right. Now you can see this portion. Now it is showing 0, but the pressure has increased on this region from 150 plus to 160 plus 167. Now, now for this pressure, the design will be performed as usual. So what program has done with that conversion, it has changed the load cases are included here and converted into a load case, and that case is brought back here with a scale factor 1. All the load factors are with the load case itself. So here, no further factoring of the loads, and this will be the load is you'll be using the design. So it has used the default design, but in the preferences for the load combinations, you can select this case, but in your original model, these will be used. You need to ensure that those are selected, and then you perform the design for this. So rest of the things are the same. Okay, so these are the two common foundation design related issues that we wanted to demonstrate in this webinar. I hope it was helpful to you. I think there are some questions. Let me try to answer them under the Q&A. Yes. Yeah, there is a requirement for the pile cap. Yes, we will do it in another. Definitely, we will consider doing it. Yeah. So that is a question. Is it possible to transfer spectrum forces from two different models? Now, it is to be understood that response spectrum analysis based on model analysis, right? Model analysis are different. I mean, model analysis results are different for these two different systems. So we cannot combine such systems unless you combine the ETABS itself in a single ETABS model with multiple towers, right? That response spectrum can be imported, but I think in the webinar itself, I have suggested the other way to handle the response spectrum, which would be much more easier, and it will also be useful in the uplift analysis also, which you would likely encounter that cannot be used in the uplift analysis. Okay. Overturning and sliding, we are not modeling for that, but overturning is checked in the ETABS itself. We have the overturning moment reported in the plots, story response plots, that you can check. Sliding is something you'll have to find external to the program. We are not modeling any friction, but I think friction in a way with the spring stiffness, lateral spring, which we applied in the U1, U2 direction, from that also we can obtain, but I think it's better checked the way convenient for you. So program does not report these two checks in the safe program. Yes. The walls in ETABS can be divided to have the distributed joint loads along the length of the wall. That is optional. Um, the current way which I showed in the model, which is not meshed, so only two joints at the ends of the wall, just having the force. More or less, it should be the same, but you can have that refinement if you want. So thick shell thick is used for the raft because we want to consider the shear deformation because it's a thicker shell, and that should be always considered. But it is a simplification that we make for the analysis. Like for slabs and walls, shell thin should be okay. We can ignore that, but you can always consider if you want. The other option is okay for the lateral spring stiffness, which I used. You can also use the advanced modeling options and perform a 2D plate analysis, provided that there are no significant in-plane forces acting in the raft. When you're modeling, some people would like to model the vertical elements above the raft. So in this model, I use only the joint loads. If these vertical elements are modeled, a 2D plate is not recommended. So you should perform always a 3D analysis with sufficient lateral supports. That's our recommendation. But those simplifications you can always make on that basis. Okay. Strip widths are arbitrary, right? So conservatively 1 meter, some people will use, but that is up to them. But you can use 1 to 1.5 times or up to 2 times the depth of the raft on either sides, right? So that way, for the left and then for the right separately, you can calculate. So let's say 1 meter depth of the raft or thickness of the raft, then on the left 1 meter, on the right 1 meter, that makes 2 meter wide strip. You can take 1.5 times and 1.5 plus 1.5, that makes 3 meter wide strips, total strip width. So yeah, you can decide on that. So there is no difference between the column strips and middle strips as far as the design is concerned. This particular differentiation is useful in the PT, where you can provide distributed or concentrated tendons in the column and middle strips. That's the useful. But RC slab or the mat, there is no difference. Yes, you can have all the all as column strips if you want. That is a common question related to the varying levels in the foundation system, right? Uh, I think that is something you need to decide because SAFE is focused only on that one plane, which is a datum plane, where we have created the raft system. So any variations, if it is significant, then you will have to use the ETABS itself for such uh, variation in the levels as well as how they are connected. So all of this can be modeled only in ETABS, not in SAFE. For most cases, SAFE should be sufficient. Okay. Yeah, tension anchors, you can apply it as spring and then you have to perform a nonlinear analysis similar to what we did in the Uplift example. But please send us your queries specifically on this. We will help you with that model. A response spectrum analysis results can be imported the similar way how we included the EQX and EQY static results. It is totally fine, but only when we are concerned about the uplift or more specifically on the uplift, where you have to do a nonlinear analysis, then this spectrum results are not that useful. We'll have to convert into linear static in the EABS itself and bring that result into the safe, similar to equivalent static. Yeah, that is a question regarding the FEM design basis and the strip based. There is a difference. Yes, FEM uses the moments to report the rebar required directly, whereas the strip based will also include axial forces, if any, present in that. So it will be much comprehensive design and is what recommended. So we will have one more session on the floor slab system there. We will cover the um, cracked section analysis in detail. Yes, definitely we'll have one more session on that. There are questions related to ETAB specifically. You should please write to us at support@csiespl.in, where we will help you with your specific queries. Please feel free to write to us. Yeah, if soil investigation reports are not available, I think new codes are giving you some guidance. You will have to use some assumptions, and that should be accepted by the peer reviewer like that. But a soil test report is almost mandatory in the new codes, as far as I know, even for smaller buildings. Vertical offset option is given in the program because it is used in the PT slab to model these uh, level differences in the slabs and then to have the tendon passing through those variations. So that is a typical use case. Yeah, stiff property, the area which can be used to model the junction, the stiffer portion of the raft. It is arbitrary that you need to decide and use. But I skipped that part. I would have used, but to save some time, I skipped that. It is optional and it is up to the user to decide on that. You can always model at the column locations. That would be the size of the pedestal or the column. Yeah, I think I have answered most of the questions. Some of them are repetitive, but if anything specific to your model, I think it's better you write to us so that we'll have a look at your model and other specific queries and answer them rather than in a generalized answering this. But this demonstration was to cover the general use case, which is the combining of models and the uplift we wanted to demonstrate in this webinar. Hope it was helpful. Thank you all for joining once again. Let's meet you in another session. Have a great day ahead. Bye.